Welcome, everybody. I hope you're all well. Today is a super warm summer day, and even the office is getting kind of hot, but we're going to get through it. So today I want to talk about a particularly practical topic that you will necessarily encounter whenever you are trying to do static program analysis on, let's say, a managed code language. So that basically concerns all kinds of languages that are running on some sort of virtual machine. So typically Java, but you will also see the same in .NET and Python and so on. Actually, almost every programming language these days has some reflective capabilities. So reflection is the topic of the day. And in many of these languages, you also have custom class loading, or in general, some runtime instantiation of potentially auto-generated code. And the question is, of course, how do static analysis deal with this? And that's a topic that I started to work on a little bit more than 10 years ago. Back then, this was a topic that pretty much everybody thought wasn't really solvable, so everybody was just avoiding it. Basically, that meant whenever there was a reflective call in a static analysis of a program, people would simply pretty much ignore it and just not handle the code that was being called reflectively. But I found this very unsatisfactory, and I thought somebody should do something about it. And so we did a large-scale study and actually also implemented a tool that solves the problem to at least some extent, and I will be talking about that. And back then I was really, really happy about it because it meant that we got a paper into ICSI, one of our top conferences. And back then it was even at Hawaii, so I actually got to fly there, which was really exciting for me as a young postdoc. 10 years ago, one could also do this without, a bad conscience, at least not a big one. Today, I'm not sure this would even still be possible, but that's one of the nice perks that you get when you go into academia. Typically, we have all of these nice conferences at nice places that one gets to travel to. We have to see how that evolves, though, over the next few years. Anyway, so you see the title of the paper. So this was about taming reflection, aiding static analysis in the presence of reflection and custom class loaders. So we designed an approach that does just that, right? So it's not totally solving the problem, but it aids in analyzing programs that have reflection. We've already seen these slides at the beginning of DECA 1. So I told you that the most important data structure that you need to conduct an interprocedural whole program analysis, or also demand-driven analysis, actually is a call graph, right? And a static call graph is a static abstraction of method calls that may execute at runtime, right? And you've seen this abstraction. So methods are nodes, calls are edges. And we also discussed that this is a flow insensitive representation. So execution order is not taken into account. And in fact, for anything that I will describe today, execution order also won't matter. And I also showed you this simple example here, right, where we have some example program, and this would be its call graph representation. I guess the details of this are not important here right now. What is important is that we can have classes that use reflection, as you can see here. So basically, what all of this code in the main method here is doing is pretty much equivalent to this call here, right? So essentially, we have these three statements, and they first of all load the class evil, and this is here actually captured as a particular class object. So this is how reflection works in Java. First, you create an actual object that represents the class that you want to operate on. Then in a second step, somebody or the programmer here fetches this particular method. So it's the doEvil method, in this case with a single parameter of type connection. That's what this is stating. So we just learned that C here is actually a connection object. And then this returns again an object representing this particular method. And then using the invoke method in the API, you can actually invoke this method that is represented by M. And here we're actually invoking it using this particular connection parameter that we see here. And the first parameter here is actually null because, as you can also see in the signature, doEvil is actually a static method. And when you're calling a static method with this API, because the static method has no owner object, so to say, you have to pass null as a first parameter. And yeah, so basically these three method calls are equivalent to this method call here, but the main difference is that here, a static analysis, it sees the class name, it sees the method signature, so this can all be easily resolved, right? But here on the right-hand side, well, it's still somehow encoded, but it's not quite as simple, right? So we have these different strings, we have these type objects here that really represent the particular types, and these strings could even be constructed, right? So this code that you see here, it's already hard to analyze, but what do you do with code that actually looks like this, right? So where the parameter, or one of these string constants here, it's actually not a constant, but it's dynamically loaded. In this case, it's even loaded as a command line argument, and this is actually really impossible to precisely analyze statically, right? I mean, what do you want to do as a static analyzer? I mean, you could guess what kind of methods this call is going to, right? In fact, there are approaches that then try to look at a certain set of classes and try to see which of them do have a doEvil method at all, and this way you can try to approximate it. But this is basically the best you can do, right? Because the string is just not part of the program, and then yeah, there's really nothing you can actually do to resolve that statically. And nonetheless, we would like to actually find such calls because they can be important. For instance, here in this contrived example, I wanted to show you why this might be important for a type state analysis, for instance, right? So let's assume we want to conduct a type state analysis that detects whether somebody is potentially writing to a closed connection object, right? And so here we have a connection that is being established and it's also being written to. And in fact, the object is being closed, like you see here, right? So this is issuing a call to close. So here we have a violation of this property, and a static analyzer should actually find this and signal a warning down here. But if you miss this call, that's never going to happen, right? Because then also this c.close call is never going to be found. And like I said, this is a contrived example, but in more complex applications, you definitely do see such cases, and they can also be, you know, safety or security sensitive. So it definitely matters a lot to analyze this reflectively called code. I will still show you some statistics in the end of this presentation. So because this is in full generality an impossible to solve problem, I will actually here present a pragmatic partial solution that already goes a long way though. Why is this important? If you look at current malware, and this is actually malware that was already current some 10 years ago, but this kind of malware still exists, then malware will also use reflection for obfuscation purposes. So what you see here, for instance, is real-world code taken from a real-world malware app, an Android app, that was actually trying to send out a text message. So that was a pretty big thing 10 years back. So then Android apps were actually monetizing by sending premium rate SMS messages over your phone. So basically an SMS wouldn't cost you what it normally costs, but it would cost, I don't know, a couple of euros. And the surplus would then directly go to the attackers. That's not that simple anymore today. There are operating system mitigations that actually prevent apps from doing this. but back then that was entirely possible. And then to hide what the app was actually doing, these apps would actually use reflection to encode these certain method calls that would then allow them, for instance, to bypass certain checks in Google Play or also some other app stores. At least that was the intention. And there are a number of important reflective calls that people use for this and other purposes. So you've already seen class for name, which is used to actually load a class instance. I've shown you method.invoke, which is then used to actually invoke a given method. But there's also class new instance, which is actually creating a new object of a class that you loaded this way. And in this case, using the default constructor. And if you want to use a non-default constructor, you first have to fetch a certain constructor instance. So constructor new instance is basically comparable to method.invoke. So similar to invoking a method here, you are invoking a constructor here with a given signature. And then this method will actually return the constructed object. And this is not the entire reflection API, but it's basically the part of the reflection API that is really essential to most static analysis. That's why I'm covering this here in particular. There are a number of reasons for using reflection, and one is obfuscation and malware I just showed you. But there are also a number of legitimate reasons, unfortunately, I have to say, because if there were only illegitimate reasons, then one could simply enforce that reflection not be used, right? But reflection is being used in pretty much almost every application. Like I said, I will show you statistics later, and that makes it harder to deal with the problem. So there is the issue of extensibility, for instance, in Eclipse, or any other IDE for that matter. I guess one can instantiate plugins without knowing their concrete class names at compile time, right? And that's true for many frameworks, right? So they allow you to instantiate certain plugins, and often these are configured not necessarily through Java code, but for instance through configuration files that contain strings, and then reflection is used to implement the actual instantiation. And if you miss these calls to these plugins, you basically miss analyzing these plugins altogether, right? So for Eclipse, that would be interesting because Eclipse is almost entirely made out of plugins. So you really wouldn't be analyzing a lot if you missed this. Then there's this issue of modularity. So reflection allows you to dynamically link with code without actually having any sort of compile time dependencies. There are more elegant ways of doing this. In Java, for instance, using interfaces that are usually also sufficient for this purpose. But in some situations, people nonetheless may want or need to resort to reflection. Then there's the issue of runtime class generation. So this is particularly complicated for the static analyzer, because here that means that the class that you actually seek to analyze, it doesn't even exist at compile time or at static analysis time. It only exists at runtime because it's only generated at runtime, right? And yeah, you can imagine that's impossible to deal with in a purely static way, right? I mean, how do you want to do this? That would be magic. And there's obfuscation, as we just saw. There's also an interesting use, let's say, of reflection that is sort of hacking around language restrictions. For instance, in Java, if you have a security manager installed, then you may not be able to access certain methods and fields, and if they are private. Yeah, I think even without a security manager, accessing private fields is actually by default not allowed. But then you can actually use the reflection API to actually disable this and get around this. If a security manager is installed, you cannot use the reflection API to circumvent this. They were that clever. Then one particular instance of this that I wanted to show you, and this we've seen numerous times in real world code, is there's really I would say it's a design flaw in the Java API, which has to do with the clonable interface. So in Java, you can mark a certain type, a certain class as clonable if you intend it to be clonable, right? So if you want the API to treat it such that you can call a clone method on it, and then the contents of that particular object will be copied or cloned, in a very natural default standard way. The problem is the clonable interface, it doesn't actually itself define this clone method. So it can happen that you have a type that you have defined as clonable, and by default this type even has a clone method, but this is protected. So maybe you can't even reach it, right? So if you want to call this from the outside, if you want to get access to this clone functionality of which you know that it is there and it is working, you can't access it, right? And so some people try to get around this. They implement some subclassing and so on. But then one way to actually get around this is actually to use reflection, because reflection will actually give you access to this clone method, and then you can actually do this invocation. So it's a workaround, it's not good style, but as so often, right, people try to take the easiest route there is. So you will find this numerous times in real-world Java applications. And in the example that I showed you with the malware, well, if you don't analyze the reflective code, then you might miss the sending of premium rate SMS messages, which is problematic, right? Because you might misclassify some malware as goodware. In the other case, with the clonable method, well, if you don't see this call, you might miss the clone functionality in your application, and depending on what your static analyzer is trying to do, that might be important, right? So for instance, there are actually static analyzers that try to ensure that if you implement cloning yourself, you are doing it correctly and you don't violate certain cloning principles. I actually wrote a paper on that myself some years ago. And then this static analyzer should probably be able to take care of these calls, right? So just to recap on reflection in general, sometimes they're perfectly good and sometimes not so good, but still legitimate reasons for using reflections. And also to load classes or call methods by name, using a string in general, and potentially the string can even be dynamically generated, right? Often it's not, often it's actually statically in the code, or it's at least loaded from a configuration file, but sometimes it can even be dynamically constructed. And when a static analyzer omits call edges for reflective calls, then it can produce unsound or incorrect results. In particular, typically you will have bad recall, so that means your analysis won't find everything it should find because it's simply not seeing all of the code. But in some unusual circumstances, you can also get imprecise results because you're, for instance, missing certain strong updates or so. That could also be a possibility. But in general, there are situations where it is impossible to resolve reflective calls at compile time. So that also tells us that a purely static approach to this problem, it can maybe go a long way, but it can never solve the entire problem. So a purely static approach is never going to work 100%. So maybe it may make sense to actually think about an approach that is not purely static. And that then brings us to the design of our particular solution that I also presented in this ICSI paper. This solution is called Tamiflex, and I will present it to you in the next video. I will see you then.